At some point in our data science journey, we have to acknowledge that we cannot always get our data through a nice little file on our computer, but instead have to resort to some SQL database. So this is why I've put together this getting started guide that shows you how to establish a connection to a database and how to upload and extract data from that database. And also I'll show you how to assemble SQL code from R, or how you might be even able to avoid having to write SQL code in the first place. And finally, I will also teach you about transactions, which are a fundamental tool to ensure database consistency. And in case you don't know me, my name is Albert Rapp. I am a mathematician and data scientist, and on this channel I help our users with typical data science tasks like connecting to databases. Let's check out how that works. In my Quarto file, I have already put in a code chunk that loads the two packages that we want to use in this video. First, there's ODBC, which stands for Open Database Connection, which is an open standard that allows you to talk to all kinds of databases, whether that's SQLite or Postgres or Oracle. You can use ODBC for all of them. Regardless of what kind of database you have, you will also use the DBI package, which stands for Database Interface. Basically, this second package allows you to use the same set of functions regardless of how you establish a connection. That means regardless of what package you use to establish a connection to a database. So these are the two main ingredients that we have, and now we can start by establishing a connection. So for that, we're going to use the dbconnect function that allows you to connect to a database. For that, we need to first specify a driver, which is more or less the vehicle that can connect to a database. And here is where we use ODBC. And to be specific, we also need to establish what kind of driver we need, namely what kind of database we have. So in this example, I do want to connect to a SQLite database. So I will just throw in a name like SQLite free driver in the hope that this driver is available on my system. We'll see in a second that this is not the case, and I'll show you how to find the driver that is available on your system. In any case, there are lots more connection information that you need to connect to a database. For example, you need to know what database you want to connect to. Here we want to just use an in-memory database, which means that all the data we have right now and we'll see in the database, it will just live in my computer's memory, and the moment the connection terminates, all the data is gone as well. It's just a thing to practice with. And then also you'll need normally a server to connect to. Your database doesn't live on your computer, but somewhere else. So this is where you would throw in the URL to the server that you need to connect to. And then you might need a user ID and a password. And you might even need to specify a specific port that you need to connect to. All of these things here are usually something that you either know yourself or someone from some tech department can help you out and give you the specifications that you need to connect to your organization's database. So when we have all the things assembled, we can try to establish a connection. Let's execute this. And now ODBC tells me that it cannot find a driver named SQLite free driver. That's a bit of a shame. I guess I haven't named the driver correctly. So let me just throw in the ODBC list drivers function, and this function, I make this into a tibble, which will look nicer. Here I can see that I do have a couple of drivers for different kinds of databases on my system. For example, I could also connect to a Postgres database, but I do want to connect to something known as SQLite. So that's why I will just use the SQLite driver here. So that's the name that I need to use. So let's just throw this in here. And now if I execute this, I do see that I do have an ODBC connection, which lives in memory, and the database is also in memory. And more or less, this is just the thing that can establish a connection and talk to my database. So that's why it's common to save this into a variable called con. And you even see that when you save this variable in RStudio, there is a connection tab opening. And when there are table, you'd even see that there is some data in here that you can look through. In my case, I rarely use it, so that's why I minimize this here. So this is fundamentally how we establish a connection to a database. And here the really tricky thing is the technical stuff of knowing that you need some kind of driver and it needs to be available on your system. If for some reason you know that you have to connect to a specific database like SQLite and you don't find a driver in here when you call ODBC list drivers, then this tells you that you will need to install this yourself. It isn't that hard. You can easily Google that for your operating system. If you are on Ubuntu, it's actually pretty easy, or if you have to work on a remote machine that uses Ubuntu or Linux in general, then you could even go into the terminal and then just use the command apt cache, use the search command, and then look for ODBC and SQLite. And then you'd see a whole bunch of stuff. Let's just make this a little bit larger here. And here you'd see that, okay, this one here is called ODBC driver for SQLite embedded databases. So this must mean on Ubuntu, you'd run something like apt get install, and then you just use this name here and throw this in here. I'm not doing this here because I've already executed and installed everything, but in general, this is how you can set up your system to connect to a database if you have to. I hope for you that you don't really have to do that, but sometimes it happens that we have to do things ourselves and figure this out. So this is why I mention it here, because I feel like this is the hardest part of databases. In any case, let's just move back to our database connection that we've already established. And now let's look at some data. So let's create a new code chunk and let's use our connection and throw that to one of the db function. All of the functions from the dbi package start with db, so it's really easy to find them. And here I want to use one of the db list functions. And here I'd want to look at, okay, what kind of tables do I have in my database? And currently that's none. And the reason for that is, of course, because I have created this database myself in memory, which means that this is only something that lives on my computer. When you work in an organization, chances are that you will find a whole lot of tables in there. But in the absence of a table, let's just create a table ourselves. Let's just take our connection and throw this to db create table. And in there we can specify a name for a table. Let's just call it Parma Penguins and use the typical Parma Penguins dataset to fill that table. So as a name, let's just go with Parma Penguins. And as the fields, we'll just use the dataset from the Parma Penguins package, namely the Penguins data. So this is the data we're going to throw into our database. So let's create this table here. And now if I re-execute this list tables command, you'll see that it tells me there is this table called Parma Penguins. So now what we can do is to actually look into that table. So let's take our connection and throw that into the read table function. And in there, we can just use the Parma Penguins name, and it will tell us that, all right, right now it's empty, but it will also give us the results as a data frame. And I personally always prefer the tibble over data frame. So this is why I will always take the results that I get from a dbi function and throw this into the stibble function. So with that, we'll make some room here. You do still see that we have a table, but it is empty. The reason why it is empty is because this create table simply creates the table and the associated columns for it depending on the data that we have. Right now you do see here that we have different data types like doubles, integers, factors. All of these things need to be specified in a database table as well. So this is why this create table does nothing but check what kind of data do you give it, and then it creates the table with the specified columns accordingly. And if you then read the table, then you're left with just the columns that you have. So here you'd see that you have characters for species and island, and that's because this factor data type is something specific to R, and you don't have that as is in SQL. So that's why you might see some differences in data types here. In any case, let us now fill the table with some data. For that, we can just take our connection and throw this to db append table. This can append data to an existing table. So for that, we'll just say, okay, the name of the table that we want to append to is still the Parma Penguins table. To spell it correctly, but now that I have spelled it correctly, I can just specify the value argument. And in there, I do want to say, okay, now I specify that I want to upload this data into my database. And now if I execute this, you'll see that nothing happened. But if I now re-execute this read table code, then you see that I do get data returned. And of course, there's nothing stopping you from re-executing this once more. You could run this again, and then the same amount of rows is appended to the table again. And the nice thing about this is that you can even just throw in a subset of columns. Let's just say, okay, we want to use the bill length and the islands, and we want to upload this data here. I can do this with append table, and we'll see that we have more rows in our table now, but we'll also see that the rows that were uploaded are not necessarily complete. For example, if I were to take this output here and throw this to the filter function from the dbplyr package and check whether the island column is missing. Island is a bad column because we have used it here. Let's just go with a flipper length. Then we'll see that there are a whole lot of missing rows, and you'll see here there's a whole lot of rows that only have island and bill length, just like we specified. Okay, so that's really how you can just add more data to your database table. And also you've seen that this here always gives you the full data that is on the database table. And then if you have it locally, you can, just like we've done a second ago, you can just filter this according to some specific conditions. And here we could just say, okay, let's just take those observations that don't have a missing value in the sex column and have a bill length larger than 50. This would give us a subset of data. And then we could also use the select function to condense that down to just 2 columns that we're interested in. So this is something you could do, and you wouldn't even need to learn that much more. You just get the whole data and then you filter and select as needed. But depending on how much data you have on your database, this can become quite infeasible because you will download a whole bunch of data just to filter out a couple of things. So this is why you can specify that you don't want to get the full data, and that's what we're going to do next. Since we're working with SQL databases, we can always take our connection and then throw this to the dbgetQuery function, and in there we can specify SQL code to get the data that we want. So here we could mimic what we have specified here. In SQL, if you want to get specific columns, you will just say select and then the names of the columns. You will specify from which table you want that. In our case, the table is called Parma Penguins. And then when you want to have specific conditions like we have here, you will use the where clause. And then there you specify that things like the bill length should be larger than 50 and the sex column should not be null. And with that, if you execute this, you do get the filter data immediately, but once again, the output of that is a data frame, so that's why we're going to use the asTibble function to make this into a tibble. And as you can see here, I have used SQL code here inside of R, and it's always a bit of a pain to throw that into these string text that we have here. But that's just what it is. The thing that I want to stress here is that you can use line breaks in here. Typically, you see SQL code written like this with line breaks to make it more legible. Nothing is stopping you from doing the same thing in R. You don't have to think, okay, this all needs to go into a string, so this is why I need to throw all of these things into one long line. That's absolutely not the case, and you will do yourself a favor if you don't do that and just throw everything onto separate lines. And really, since we are working with R and you're probably familiar with the dbplyr syntax, it would be great if we can just use the exact same code but with a database connection. And that's where dbplyr comes in, and you never need to load it. So you technically never need to load dbplyr, because dbplyr is structured in such a way that it detects if something that is passed into it is a database table, then it will just do its thing using SQL in the background. Let's just take this code here and let's get the data that we need as a table. This means that we specify a new variable, let's call it table Parma Penguins, and in there we use the tbl function from the dbplyr package, which needs the database connection and the table name. And when we execute this part here, and have a look at it, it will just tell us that it is a table Parma Penguins from some database. And it will also show you a couple of rows from that data set. You will see here that there are question marks in there, and that's because these tables can get really huge in SQL databases, so that's why you will never see the full amount of rows in there. dbplyr will just show you the first 10 basically. But the nice thing about this table now is that we can just throw this into our code from before, and now because dbplyr is structured in such a way that it detects when the input is a table that comes from a database, then it will just do its thing and give you the data that you're looking for. But once again, you see here there are only the first 10 rows and you don't have the full data here. So that's why one specialty that you have to watch out for is that you need to collect the results, and for that there is the collect function. And now if you execute this, you do see here that you have everything locally now, and you do know exactly how many rows you have. And this, of course, corresponds to the code that we have just written manually. Speaking about this SQL code, you can also check out what dbplyr will do behind the scenes for you. Namely, you can just take your code and let the dbplyr package use the show query function, and in there it tells you what it used to get the data that you're looking for. As you can see, it's very similar to ours. It uses a little bit of a different syntax, but fundamentally it does the same thing. And the nice thing about this is that it will translate to the SQL dialect that you have. The thing with SQL is that if you have it not SQLite, but Postgres or something else, then things might be specified a little bit differently in these queries. And the nice thing is that you don't have to worry about this, because dbplyr will detect from the connection that you pass into it what kind of SQL dialect it needs to use. So this functionality is a huge help if you don't know any SQL, and I might do a deep dive on dbplyr in the future. Feel free to let me know in the comments if that's something you're interested in. But for now, let's move back to writing SQL ourselves, something like that, because reality is that you might have to do this yourself too, because you will get SQL code from colleagues and you won't get dbplyr code. But still, there are nice ways to assemble SQL code, and that's what I want to show you next. Let's create a new code chunk in here, and now let's throw in a couple of variables into this here. Let's assume that we have variables that tell us which table we want to access, which columns of that we want to access, and for a specific column, which values we are interested in. Let's just assume that we have something like this as our variables, and we want to translate this to SQL code. For these kinds of scenarios, the glue package is invaluable because it has the glue SQL function. In there, you can specify a string as SQL code, and you can also specify the connection. Not you can, you have to specify the connection that you're using. So in here, you can throw in the SQL code that we have. Let's just use this part here as a template. And in here, we do want to make this dependent on the R variables that we have. And the nice thing about glue is that we can just stick variables in there, and we say, okay, we want to have these columns from this table. And here we have to modify this a little bit, where species is in, and then the things that we're looking for should go into selected species here. So that's a SQL code that we could assemble. And now if we execute this, we do see here that we get two separate SQL calls now. So that doesn't really do what we want. Instead, we'd like to have all of this combined into one call. And the nice thing about this is that in the glue SQL syntax, when you use these curly brackets to use variables, you can automatically collapse factors into a comma-separated list. All you have to do for that is to throw in an asterisk in these things that you want to collapse. Now, if you re-execute this, you do see here now that you have a comma-separated list of these values. So we could throw this into a variable, let's call it query, and then we can take our connection and use db get query once again to throw in the query that we have, and we know that we want to have the results as a table. Now if we execute all of this, we do see here that first we have a warning. Let's just get rid of this. I misspelled as tibble with a dot instead of an underscore, but once we get rid of that, we do see here that we don't really get the correct results that we want. And the reason for that is that our SQL code isn't quite correct. You see, for some reason, it always just gave us a column that has bill length and sex inside of it, which obviously isn't what we want. And the reason for that is because these single quotation marks are not used in SQLite the way we want to use them here. Instead, we want to use these bill length names and sex and Parma penguins as identifiers, meaning names to look for. And we can either use double quotation marks or no quotation marks at all. But single quotation marks are always reserved for values, just like we've done with Adderley and Chinstrap here. So clearly, the glue SQL function did the right thing for the selected species here, but not for the identifiers that we use here. And the way to fix that is to just throw the things, the identifiers, into backticks. And that way, if we look at the query, it will use double quotation marks instead. And now if we re-execute this whole code, we now see that we get the data that we want. So the glue package offers you a really neat way to assemble SQL code using variables from R And I cannot stress how much easier it is to use this syntax here to do the collapsing with the asterisks and the IDs with the backticks compared to when you want to assemble SQL code yourself manually with the paste function. Do yourself a favor, don't try to assemble something like with paste and then select, and then you have to throw in a variable here and then another string and so on. This is not fun at all, and it isn't legible in the end. This, on the other hand, once you know about the special notation with the asterisk and the backticks, is really easy to read and it will save you so much work. So I really encourage you to go with this mode instead of using the paste function. Alright, this video is getting long. I only wanted to stick to the very basics here, but I do want to mention one more thing which I think you should definitely know about, and that is transactions. Let's create a new code chunk for this, and now let's throw in the connection and throw that to dbBegin. With this dbBegin function, you can start a transaction. Instead of me explaining what this does, let me just show you exactly how to use it. So let's just start a connection, and then let's just use our code from before where we have appended data here. Let's just throw this in here. Also, let me grab this data here so do we know what data we have currently in our table. And then let's just get rid of that here. So right now, I haven't done anything other than starting the connection. And now currently we have 1032 rows in our data. Just like we did before, we can append a table here. And now if we execute this part here, we do see here that we have more rows inside of this. So right now our database table has way more rows than we had before because we've appended data to this table. But watch what happens when I do use the db rollback function now. I execute this and now I check out how many rows do I have in my database table once again, and we are back with the 1000 rows that we started with. And the reason for that is because we have aborted our transaction here. Basically, you start a transaction with dbBegin, and there are only two ways to close a transaction. Either you revert all of your changes that you have done since dbBegin, and the name for that is rollback, or if you don't want to roll back and we throw this data back there again, we do see that we have these almost 1400 rows. But now instead of rolling back, I want to commit to the changes that I've done. And now if I execute this and now recheck how many things do I have in my table, I do see here that the number of rows is final now. I have committed to my changes, and this is why the rows won't vanish anymore. Unless, of course, I manually go in and take them out. That's, of course, they are not immutable. But the thing is that with these transactions, you can do a couple of changes to your database. And when something goes wrong, you can just revert everything to the way it was when you started. That's a really important feature when you have to update rows or insert more rows. Then it is really important that you work with these kind of transactions, because you can then revert back to normal in case something goes wrong. The worst thing that can happen to you is that you do a couple of queries with your database and upload the new data, and somewhere in between something goes wrong and you have no clue what data did get through, what data didn't get through, what is your database quality now, what's the data that is in there, which data do you have to manually get back in there. That's a huge pain if you run into this. So this is why you don't want to even run into the chance of having such a problem. And this is where these transactions come in. It's an either everything works or nothing works kind of situation. And to make this more precise, let me give you another example. Let's just throw in a new code chunk. And in this code chunk, I want to take a vector that specifies the allowed species that are allowed in my species column. And now I will create a new table that enforces that whatever you write into the species must be one of these three things. So that's why we assemble a new query using the glue SQL function that we've just learned. And in there, we use the create table SQL code. We name this new table Parma Penguins New. And then we have to specify all the columns that are inside of this column. And the first thing we specify is the species column, which is a text column that cannot be null. And we check that the species is one of the three allowed species. And for the other columns, we just specify island is a text column, bill length and bill depth are real numbers, flipper length and body mass are also just numbers, sex is a text, and year is an integer. So that's how we have assembled a new query. Of course, we need to specify what kind of database connection we have for glue to get the SQL dialect right. And once we have that, we can throw our query into db execute, which will just perform such a query where we don't get anything back. We've always used db get query because we wanted data to be returned, but here we just tell the database to do something. So this is why we use db execute. And now if we execute this, we get a 0 back. That doesn't concern us at all, but we now know that we have a new table. So if I use db list tables, then we see that we have another table now. So what we could do once again is to throw in new data in there. So let's just use the connection and use db append table. We want to append to Parma Penguins new this time. And in there, we can just use the Parma Penguins data, just like we've done before. This worked perfectly fine, but watch out what happens if instead of using the correct Parma Penguins data, we use some data that has a wrong species. Let's just create a table that as a species uses something weird. Let's just go with that. Then in this case, you do see here that you get an error. It says constraint failed. You tried to upload a wrong species. So from this point of view, everything worked kind of nicely. And that's really cool that you can put in these conditions on columns to check for data quality. That's a really neat thing. But imagine that you try to execute these two commands in an R script consecutively. You might hope that all of them work nicely, but this isn't necessarily the case. And when you run this in a whole script that does even more things, then you will soon run into the problem of not knowing where the error occurred, which specific thing you tried to do made the error happen, and what are the things that you now need to do manually instead of just using your R script. So that's why we use transactions that will either make sure that all things succeed or none of the things. Let's just take this and throw this into a new code chunk here. So in this code chunk, I do want to show you the pattern that you need to use to make sure everything works nicely. So first you start a transaction, you use db begin. And then you need to try to execute all of the operations that you want. And for that, you will use try catch. And in there, you just specify all the R code that you do want to run. If all of these things run through without a problem, then you can just execute the db commit function. At that point, when this row in your script is reached, this must mean that all of the previous things ran without a problem and you can commit to all the changes you have done since you've started db begin. But if at some point there appears to be an error, you need to roll back. And within try catch, you can say, okay, in case of an error, execute the following function. And in this function, you specify what needs to be done. Namely, you first want to roll back. That's the first thing you want to do. But you also do want to give some warning message. And for that, I like to use the CLI package and use the CLI abort function to throw in an error message. So what you could write into this is say something like data couldn't be uploaded successfully. And there was the following error. And then you can even use the glue-like syntax inside of CLI abort. This is one of the reasons why I like to use this CLI package to give these kind of error messages. And now if you execute this whole code chunk, you'll see that we run into an error. We get data couldn't be uploaded successfully. There was the following error. And then we see here, there is this constraint failed thing. And if we look into our database table, so let's just throw this to db read table. Then of course we need to specify what table we want to look at. And if we specify this correctly and throw this once again to table as table, then we see here that we have the original data set that we've uploaded once. So that's why we have 344 rows, but we don't have 680 something rows, which we would have if this line of code actually became permanent. Because here we uploaded the data once more, so we should have 600 something now. We could even re-execute this a couple more times, but we see regardless of how often we do, and we know that this code will work regardless of how often we do this whole try catch thing, we'll always be left with the fully intact database, and we can be sure that nothing was changed. And that's the power of these transactions. I know that it's a bit more effort to use this try catch and then do this db commit or db rollback, but I do think that's a really safe thing to do. And in the long run, it will save you some nerves and will make your life a little bit easier. Now with that, we have not covered everything there is to know about SQL and R and the combination of both, but we did learn a good amount of basics. If you have any specific questions, feel free to drop them into the comments so that I might make a new video about your specific questions or more SQL stuff. But for now, all that's left to say is thank you for watching, and I will see you next time.